So now we will see hermite polynomials. Hermite polynomials were first developed by Laplace and later worked on by Chebyshev to their current state. Hermite polynomials can be defined as a classical orthogonal polynomial sequence. By polynomial sequence, we mean that they are a sequence of polynomials as a solution, and by orthogonal, we mean that every two terms are orthogonal to each other, meaning that if you integrate them over real space from minus infinity to infinity over a weighted function, then their value will be 0, and this we will see later as a property of hermite polynomials. Hermite polynomials have several applications. So they arise in Edgeworth series, and those are known as probabilist hermite polynomials. And they also arise as eigenstates in quantum harmonic oscillator, and those are known as physicists hermite polynomials. First, let us see probabilist hermite polynomials. We will represent the function as he of n of x, which is the nth polynomial in terms of x, which can be written as minus 1 to the power of n into e power x square by 2, nth derivative of e power minus x square by 2, which can also be written as x minus d by dx of whole to the power n. So now we come to physicists hermite polynomials, which can be written as minus 1 power n into e power x square and nth derivative of e power minus x square, which is again written as 2x minus d by dx whole power n. These two are not exactly the same because they can be rescaled into each other. So if you want to rescale physicists into probabilists, we use this formula equal to 2 power minus n by 2 hn of x by root 2. And if you want to rescale probabilists to physicists, we use this. Now let's see first few polynomials in probabilists. So he of 0 of x is 1, he of 1 is x, and he of 2 is x square minus 1. For physicists, of 0 is again 1, of 1 is 2x, and of 2 is 4x square minus 2. How we got this is by simply substituting n in the given equation here for both the series. And now we'll come to the properties of hermite polynomials. Before that, we need to know that since these are a sequence of polynomials, they're basically the solution to a differential equation, a generalized differential equation. Here the equation is u double dash minus xu dash is equal to minus lambda u. Here u is our function of x and lambda is a constant. This is for probabilists, and for physicists we have u double dash minus 2x u dash is equal to minus 2 lambda u, where again u and lambda stand for the same thing, a function and a constant. Now the properties of hermite polynomials. First one is orthogonality. As we previously mentioned, the sequence of polynomials are orthogonal. So if you integrate them from minus infinity to infinity and multiply two hermite polynomials over a weighted function, then the value will be 0. This weighted function is e power minus x square by 2 for probabilists and e power minus x square for physicists. To simplify it, you can write it as root 2 pi n factorial into Dirac-Delt's function mn. With Dirac-Delt's function, as we know, it is 1 when m is not equal to n, and it's 0 when m is equal to n. Similarly, we can write physicists as root pi into 2 power n into n factorial into Dirac-Delt's mn, where it's the same, it stands for the same thing. So that means from this property we know that every two polynomials in the sequence are orthogonal. Second, the hermite polynomials are complete, which means they satisfy the following equation. So if you take a mod of the function and square it over a weighted function, then the integration from minus infinity to infinity will be less than infinity, so it's bounded basically. And here the inner product of the function fg will be given by f of x g of x into w of x integrated over minus infinity to infinity. Finally, to get our hermite polynomials as a sequence, we have certain recursive functions. So if you want n plus 1 of x, then you can write it in terms of n of x and n dash. So he n plus 1 of x is x hen of x minus hen of x whole derivative. And similarly, hn plus 1x is equal to x into hn of x minus hn of x derivative. So these are the recursive functions to generate the hermite polynomials. One last topic will be the contour integral of these polynomials. So you can write them as integrated over a contour over the origin. So you can write probabilis as n factorial by 2 pi I, contour integral of e power tx minus t square by 2 whole divided by t power n plus 1. And for physicists, n factorial by 2 pi I, contour integral of e power minus t square plus 2tz by t n plus 1. As we can see, the equations are very similar, but they differ basically in their constants, which will give us different values. But again, the power of the values and the degree of the equation will continue to remain the same. So this is Hermite polynomials.